Good day, everyone. For today's lesson, we're going to talk about the Rayleigh-Taylor instability. So, what comes to our mind when we hear the word the Rayleigh-Taylor instability? Okay, or what is Rayleigh-Taylor instability all about? Rayleigh-Taylor instability is all about the interpenetration of materials that occurs whenever a light fluid pushes on a heavy fluid, according to Rayleigh 1883, Taylor 1950. It is the dynamic process whereby the two fluids seek to reduce their combined potential energy. The ensuing turbulence and mixing has far-reaching consequences in many natural and man-made flows, ranging from supernova to inertial confinement fusion capsules. So it means that the Rayleigh and Taylor instability that the light fluid will going to push the heavy fluid, which is the light fluid will going to be sink and the heavy fluid will going to rise. What are some example of the Rayleigh-Taylor instability all about? One of its example is the stellar gas, which is a very large scales which push out of the galactic plane through the magnetic fields and cosmic rays, becomes RT unstable or Rayleigh-Taylor unstable because of the driving beyond its natural scale height. Another one, it also occurs at a very small scales. We have the snapping shrimp, which also produce most of the ambient noise in subtropical shallow waters through the world, and it produced their sound through collapse of a cavitation bubble, and it generated by a water jet formed from rapid flow closure. So this bubble is going to destroy, that is because of the Rayleigh-Taylor instability. Similarly, the RTI limits the driving pressure in the collapse of acoustically forced bubbles in sonoluminescence phenomena. So again, the snapping shrimp bubble is being destroyed because of the RTI or the Rayleigh-Taylor instability. So this RTI or the Rayleigh-Taylor instability has a profound effect on the Earth's climate. It's because the winds of the coast of Greenland and Iceland drive evaporation of the ocean surface, making the upper layers saltier and heavier. That means the heavier fluid will going to sink or going slowly down. Also, they generate descending plumes that drive the abyssal ocean circulation, which in turn acts as a heat pump transporting warm equatorial waters up north. Without ocean overturning from RTI, or not because of the RTI, northern Europe would likely face drastic drops in temperature, or in the northern temperature is not balanced. Before I proceed, please watch this short video for more information about the Rayleigh-Taylor instability. And it will show on how the heavier and lighter were going to rise and down.
Have you ever wondered why your iced coffee looks kind of like a nebula? I'm Nicole Sharp, and this is FYFD. You've probably noticed at some point that crazy turbulent motion that happens when you pour milk into tea or coffee. You're combining fluids with different densities, and that's a breeding ground for the Rayleigh-Taylor instability. Let's look at a simplified example. Imagine you have two fluids sitting on top of one another. We're on Earth, so gravity is acting downward. If the upper fluid is less dense than the lower fluid, nothing happens. But say we switch them so the upper fluid is denser and heavier than the lower one. The lighter fluid is going to rise while the heavier fluid sinks. This interface between the two fluids is going to get distorted, and because the heavy fluid will keep trying to sink while the lighter fluid rises, the interface is only going to get more and more distorted as time goes on. This is what Lord Rayleigh realized when he first described the instability. Later on, G.I. Taylor recognized that the same thing happens if you accelerate a less dense fluid into a more dense one, which is what happens in underwater explosions or the aftermath of supernovas. There are a few distinctive shapes that show up in the earliest stages of the Rayleigh-Taylor instability. Here you can see how a single finger along the interface forms into a spike and then a mushroom shape. These fractal swirls appearing along the edge are actually another instability, the Kelvin-Helmholtz instability. Very quickly, the fluid motion becomes incredibly complex and turbulent, which is good for mixing milk into your drink, but it makes it hard to catch what's going on. Let's try to slow things down some. Here I've filled 2 cups with a mixture of corn syrup and water. Corn syrup is only a little denser than water, but it's about 1,000 times more viscous. If you do the full mathematical analysis of the Rayleigh-Taylor instability, viscosity does have some effects, but mostly what it does is decrease the growth rate of the instability. In other words, it slows everything down. The yellow glass contains the denser mixture. Now we remove the barrier and watch what happens. Even with the high viscosity, things go quickly. Fingers of the lighter blue fluid push upward and the yellow fluid sinks. The fingers deform, overturn, and mix. The high viscosity keeps the Reynolds number low and prevents turbulence, which is why the mixed green region isn't very wide. With milk and coffee, the lower viscosities allow more turbulent mixing, which is why they don't settle out the way the corn syrup does. So, there you have it. Next time you're in
So let's check the historical development of Rayleigh-Taylor instability. In 1880, as part of an effort to better understand the formation of cirrus clouds, Lord Rayleigh first derived the interfacial motion that occurs when a heavy fluid is supported by a lighter one. He considered the idealized case of 2 incompressible, immiscible fluids in a constant gravitational field. While in 1950, Sir G.I. Taylor recognized what's really discovered, which is the interfacial instability, also is being occurs for acceleration other than the gravity. The classical case, it involves constant acceleration. However, RTI also occurs for the time-dependent accelerations whenever the accelerations is directed from the light to the heavy fluid. Since the 1950s, numerous experiments and numerical simulations have been conducted for both constant and variable accelerations in an effort to be better understand what is the Rayleigh-Taylor instability scaling properties and mixing rates. Experts in the experimentalists have tried to measure under a variety of conditions, which is the major challenge in any experiment is to precisely characterize the tiny initial perturbations. Interfacial perturbations occur naturally at all wavelengths up to the dimensions of the experimental apparatus. Hence, most experiments don't satisfy the first inequality. So these are some strategies that experimentalists have employed are, which is the first one, we have the accelerating a tank of a light over heavy fluids downward. We have also the rotating a stably stratified tank of fluid by 180 degree. In addition, we also have the withdrawing a plate separating a heavy fluid above a lighter one. We also have flowing two fluids past a splitter plate. We also have a magnetic levitation of paramagnetic or ferrofluids. So most of those experiments performed to date have returned values. That would be all of my discussion. Thank you and God bless and have a nice day.